In this video, I'd like to explain the following mathematical notation called limit notation in the context where you have an equation of the form y equals ax squared plus bx plus c. Before I start, I want to show you that even though I'll be changing the values of a, b, and c in the quadratic, that changing b and c won't change the following behaviors of the graph. Notice that when you move a point a on the parabola to the right, the graph goes up. Notice if you move the point way to the left, the graph also goes up. Notice this behavior will not change if I change the value of b or c. In fact, c moves the graph up and down, but doesn't change the fact that when you move to the right, the graph goes up, and when you move to the left, the graph goes up. Likewise, changing b moves the graph, the parabola that is, around a bit, but still doesn't change the fact that the graph points upward at both ends. Now let me fix b and c to be some number and show you what happens with a. As long as a is positive, you'll still have the same behavior that the graph points up on both ends, but as soon as a becomes negative, this changes. In fact, once a is negative, as you move the point along the parabola, movement to the right has the point going down. Also, moving to the left has the point going down. So as long as a is negative, movement to the right or to the left on the parabola will have the effect of moving the point downward. Let's go back to where a was positive and keep a, b, and c fixed, and let's look at what it means numerically with the inputs and the outputs of the function as you move to the right and to the left. As I move the point to the right, you'd notice that movement to the right has x increasing. Watch the value of x increase as I move to the right. Also notice as x gets bigger, my output f of x gets larger as well. This is what it means for a graph to go up as you move to the right. In fact, when a is 1 and b and c are 0, the quadratic equation becomes y equals x squared. Here is a table showing you what happens to the outputs of the function as the inputs get larger. As x gets larger and larger, it goes from 1 to 10 to 100, etc., the outputs f of x also get larger, 1, 100, 10,000, etc. So when you have a graph that goes up to the right forever, numerically this means as x gets larger, f of x will get larger. If you look at the following notation, this notation describes the exact behavior we just discussed. LIM is short for limit. This is read the limit of f of x, which basically means what is the behavior of your outputs, the function values, that's these numbers, as x approaches infinity. What it means for x to approach infinity is simply that x gets larger and larger without bound, like we did in the chart, 1, 10, 100, 1,000, 10,000. If I took a point on the parabola and scrolled to the right, as x gets bigger, y gets bigger. So when this statement says the limit of f of x, it's saying what's happening to the outputs of my function here is that they're getting larger, but in the positive direction. We denote this by saying that the limit is infinity. This means my outputs, f of x, are getting larger and larger in the positive direction, infinity, as long as you're plugging in successively larger x values, meaning x is getting larger and larger, or x approaches infinity, as we did here. Let's look at what the notation would look like if I wanted to tell somebody that I have a graph that when you move to the left, it goes up forever. Well, it's almost the same thing as before, except if you look at the x values of this point A, let me move them over here, you'll see that the x values will be negative because I'm moving to the left. Also notice, the further I move x in the negative direction, that your outputs f of x will remain positive because the graph is above the x-axis, but get larger and larger. Again, as x gets further in the negative direction, my outputs f of x get larger and larger. You can see this with the coordinates of the points, or if you'd like, you can look in the table over here. As I plug in numbers further and further in the negative direction, negative 1, negative 10, negative 100, meaning movement to the left on the x-axis, my corresponding outputs f of x grow larger but in the positive direction, 1, 100, 10,000, etc. This is the notation that would describe this. If you compare it to the notation I had previously, it's exactly the same, except I changed it so that x is approaching negative infinity. This arrow is read approaches. So this is read x approaches negative infinity. What that means is if you were to move to the left on the real number line, and moved from x equals negative 1, negative 2, negative 3, negative 4, and did this forever without bound and never stopped, this question says, what would happen to my corresponding outputs f of x? As x gets large in the negative direction, as I've done here, -1, -10, -100, the answer to the question is that f of x, my outputs, get larger and larger, but positive. So we say again that the limit is infinity. This is read, the limit of f of x as x approaches negative infinity is equal to infinity. It turns out there's still two more things I'd like to do with this notation. The two results I just explained were what happens to a quadratic when a is positive. Remember that if you're discussing the end behavior of a function, it does not matter what b and c are in the problem. It only depends on whether a is positive or negative. As long as a was positive, that may change the numbers over here you can see, but it does not change the pattern of the numbers insofar as x gets big in the positive direction, the outputs get big and positive, and if x gets big in the negative direction, then your outputs get big in the positive direction. This result would change if I made a negative. Watch what happens when I move a to a negative number. Now all of a sudden, the table changes and the graph changes. As soon as you make a negative, things change so that if you were to move a point on the parabola to the right, the graph would go down. Also, if you move to the left, the graph would go down. Let's investigate what that means in terms of the inputs and outputs. As I move to the right, watch what happens to x and f of x, my inputs and my outputs of the function. As I move to the right, x will get bigger and bigger in the positive direction. As we did before in the chart, x gets larger and larger, but remains positive. And when that happens, watch what happens to my function values f of x. As I move to the right, you'll see x getting larger and larger in the positive direction, but you'll also see that my y values are negative this time. I like to say they're getting larger in the negative direction. Because I'm graphing in a small window, it may be best to look over here at the table and look at what would happen if I was to trace a point along the parabola for really large x values such as 1, 10, 100, 1,000, etc. Your outputs, f of x, would get very, very large in the negative direction. This is the notation that would say that. For these data, notice x was getting larger and larger, but positive. We say that by saying x approaches infinity. Then the notation asks, what is the limit of your outputs? What's happening to your outputs of your function as x gets bigger in the positive direction? And the answer is that the limit is negative infinity, meaning they grew without bound, but they were negative. Negative 2.5, negative 250, and they keep getting larger and larger, but negative. Remember, this would be true for any value of b or c. As I move b and c, you'll see that these numbers change. However, they still remain negative, and they still get larger and larger in the negative direction, provided x gets bigger in the positive direction. The last thing that I'd like to discuss is if a were negative, what would happen if you were to move a point on the parabola to the left? As I move to the left, pay attention to the inputs x and the outputs f of x. Right now, x is positive and will be getting smaller and smaller. But as soon as I move the point left of the y-axis, my x values will be negative. I want to move the point further and further to the left, and as I do so, the graph goes down. What this eventually does is makes the point in the third quadrant. And any point in the third quadrant will have both a negative x value and a negative y value. And as I move to the left, as x gets larger and larger in the negative direction, you'll see my outputs f of x getting larger and larger in the negative direction, meaning that as I move to the left, the graph will continue to go down forever. There's no limit to how negative I can make my input, and there will be no limit to how negative the output becomes. This is shown in the chart over here. Because I'm graphing in a small window, say from -4 to 8, it's difficult to show the behavior I want to show unless you look at a table of values. As x gets larger in the negative direction, -1, -10, -100, etc., my outputs, f of x, get larger and larger in the negative direction. Look how big they become. And remember, this pattern would exist for any values of b and c. This is the notation that would describe that pattern. Since a was negative, and I was moving the point to the left on the parabola, my x values were approaching negative infinity. We write that as x approaches negative infinity, which really means we're just letting x get really, really big, but negative. And that would happen whenever you move to the left on the real number line. When I move points on the parabola to the left, my outputs, or my y values if you will, become negative, and grow larger and larger and larger as we showed in the table. So the answer to this question, what is the limit of f of x, would be that f of x is getting larger and larger but in the negative direction. You should note, however, that many mathematical textbooks would consider all 4 examples in this video as such that the limit does not exist. This is because the definition that most textbooks go by are that limits have to be a real number. Infinity and negative infinity are not real numbers. This video did not allow the opportunity to see an example where we evaluate a limit and get a real result. Many times you will see the statement does not exist abbreviated as DNE for does not exist. This is not the only context for which a limit would not exist. However, it is a context for which answering the question does not exist does not give the opportunity to describe the behavior that existed in the problem. In this particular context, saying the limit does not exist would not allow you to communicate that your function values were growing without bound either in the positive direction, like these 2 cases, or your function values were growing in the negative direction, negative infinity, as it were in these 2 cases. So even though the mathematical standard is that the limit does not exist, many textbooks will allow writing answers as infinity or negative infinity, as these answers provide more information than simply saying the limit does not exist.